Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from May-June 2025. Paper 4, Variant 4. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of physics and also you can have good understanding of these exam questions. Today's video is the first video and a lot of more videos for 2025 will be uploaded very soon. And also I have uploaded a lot of past paper questions and the solutions on the channel, so you can search for those videos. And if you have any questions, please leave your questions in comments and I will try to answer as soon as possible. Let's study together, let's improve together. Question 1, part A says, define gravitational field. And this is a typical question. You need to understand how to define gravitational field. For Cambridge A-level physics, when you need to define gravitational field, you need to simply say force per unit mass. So simply you have to say this is the force per unit mass. So this is how you need to define gravitational field for Cambridge A-level physics. And this is written very clear in specifications. So simply you have to say force per unit mass. So this is how we can define gravitational field. Part B says the gravitational field at a distance x from the center of a uniform spherical planet of mass capital M is given by the expression, where g is the gravitational constant and distance x is greater than the radius of the planet. Means the point is outside of the planet. Describe the pattern of the field lines outside the planet that represent the gravitational field due to the planet. So how we can answer? So simply first of all imagine this one is the planet. So this is our planet. So you can imagine this is not hollow. So this is planet. Now we need to draw the gravitational field lines for this one. So we need to understand gravity is attractive force. So you need to draw the arrows inwards. So this is how you can draw the arrows. So you can draw these arrows inwards. So at least 4 or more than 4 arrows you need to draw. But they have to be inwards. And these arrows also have to be equally spaced. So we can draw these arrows. So this has to be equally spaced. So very important one. Inwards and equally spaced. So if you have drawn like this, you will get 2 marks. One for inwards, arrows are pointing to the planet, and the second marks, they are equally spaced. For the second part, we need to explain why for small changes in vertical height near the surface of the planet, g may be assumed to be constant. So again, we will go back to the planet. So we can redraw this one. So this is the planet. Now let's take a point x here. So this is a point and its distance from the surface, let's say this distance, let's say this is delta h. So we can say this distance is delta h, and the distance from the center of the planet, so we can say distance from the center of the planet, let's say this distance is x. So the value of g at the surface and this distance also we can label, we can say this is the radius of the planet. So the value of g at this point at the surface, g will be equal to mass capital G times mass of the planet divided by the distance from the center of the planet. So this is at point R, and value of g at point x, we can say this will be equal to g capital M divided by x square, or we can say this is g capital M divided by, this will be r plus delta h square. Now in the question it is given to us small changes in the vertical height. Small changes in the vertical height means that this delta h is very small, is about equal to 0. So we can simply say it's about equal to 0. Or we can say if delta h is much smaller than r, then we can say that gx will be equal to gm divided by r square, because delta h is about equal equal to 0. So we can say Gx is approximately equal to this, and this is equal to approximately G at the surface. So at the surface. So it means that for the small changes, the change in height is negligible. So for any point, for example, if I move from this point to this point, and this change is very small, so the change in value of G will be very small. So we can compare those 2 points. If this change is very small, for example, delta H1, if this change is very small, then the value of G at this point, let's say this point is A, this point is at B, this point is B, so it means value of G at A will be about equal to value of G at point B for small changes. I hope this makes sense to you. Now let me show you the answer, how you can write down your answer. So here is the answer. This is how you can write down. So if you include these points in your answer, you will get 2 marks. So we have mentioned in this case, x is equal to r plus delta h. Delta h is very small as compared with r. So G is approximately equal to this one. So for small changes, G is about constant. So if you move 1 meter away from the planet, change in G will be very small. If you move 100 meter, again change in G will be very small, because value of R is much greater than value of 100 meters. So this is the main point you need to understand. And this is also very helpful for some calculations when you need to calculate value of G. Part C says, assume that the Earth is a uniform sphere. So very important, you need to understand. We are talking about specific planet now. And for the Earth, the product Gm is equal to this value. Determine a value to 3 significant figures for the radius of the Earth. 3 significant figures. So you have to use 3 significant figures in your answer. So for this one, Gm is given to us. So simply we can say this is Gm. And value of G at the surface of our planet is 9.81 newtons per kg. So this is newtons per kg, value of G at the surface of our planet. So simply we can say G, this is equal to G times m divided by r square. So we need to find out value of r, so we can rearrange this one. We can write on this is Gm divided by small g square root of this. Now simply plug in values and we can find the answer. So this is 3.99 times 10 to 14 divided by, we have 6.38 times 10 to 6. So you can also write on this is equal to meters per second square, and then if we solve, we will get our answer is equal to 6.38 times 10 to 6 meters. So this is how you need to answer. Second part says calculate the gravitational potential at the Earth's surface, give a unit with your answer. So we need to calculate value of gravitational potential. So how do we calculate gravitational potential? So first of all, you need to understand how to calculate. So this is equal to negative Gm divided by r. So it is negative. Gravitational potential due to any planet is always negative. Now simply we need to plug in values and we can find the answer. Gm, the product of Gm is already given in the last part, and the value of Gm is 3.99 times 10 to 14. The negative sign is here, and value of r we have calculated in the last part, that was equal to 6.38 times 10 to 6. So the final answer will be 6.25 times 10 to 7. Simply you can use calculator. And potential is the gravitational potential energy per unit mass. So the unit has to be joules per kg. So simply you can say joules per kg. So here is our final answer, 6.25 times 10 to 7, and here is joules per kg. So this is how you need to answer. Part D says explain why the gravitational potential energy of 2-point masses is always negative. Potential energy of 2 masses is always negative. For this one, we need to understand, first of all, imagine that this is a planet. So this is planet. Let's say the mass of this one is capital M. At infinity, so this is point located at infinity. At infinity, we take gravitational potential potential energy, this is equal to 0. So now if we go this way, gravitational force is an attractive force. So work will be done by gravitational force. As work is done by gravitational force, so the gravitational potential energy will decrease. So we need to understand, when work is done by gravity, this is equal to the negative change in GPE. So then the change in GPE is negative. If the work is done by gravity, that is equal to the change in GPE. We can also write down this one. Work done by gravity, this is equal to negative delta GPE. If work done by gravity is positive, change in potential energy is negative, mean potential energy decrease. So below 0 is negative. So the potential energy anywhere other than infinity due to mass always will be negative. So due to two masses, always negative, because at infinity we take GPE equal to 0 and lower than 0 is negative. So this is the point simply you need to understand, and this question is very common in past papers. So you have to be very clear how to answer this type of question. Sometimes they will ask you why gravitational potential energy due to a mass is always negative. So here they make little bit tricky. Explain why the gravitational potential energy of 2 point masses is always negative. So this is the same case. So when you bring any object from infinity to a point between 2 point masses, mean in the gravitational field of 2 point masses, work done by gravity has to be positive. Gravity will do positive work, so the change in potential energy will be negative, or we can say the work done by external agent, that work done is negative. That's reason change in potential energy is negative. So you have to be very clear about this one. So this is very simple. For example, if I'm holding this pen, if I drop the pen, what is happening to the GPE? Is it increasing? Is it decreasing? I hope you will say it is decreasing. Now think about the work done by gravity. Is the work done by gravity is positive or negative? Positive, because the gravity is down, object is also moving down. So work done by gravity is positive. So when work done by gravity is positive, GPE is negative. Now let me show you the answer, how you can write down the answer. So this is how you can write down your answer. So these points you can mention is defined as the work done to bring a unit mass from infinity to a point in the field. Since gravity is attractive, work is done by the field, means GPE decreases from 0 to negative values. So this is how you need to answer. Today's lesson we will just stop here, and the remaining questions I will try to upload as soon as possible. And if you have any questions, please leave your questions in comments and I will try to answer as soon as possible. And if you're looking for more resources such as PDF of past papers, solutions, notes and other resources, you can check Patreon. And the link for Patreon is in the description of this video. See you in next video. Good morning, good afternoon or good evening. Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from May-June 2025, paper 4, variant 4. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of physics and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question 2, part A says, state what is meant by objects being in thermal equilibrium. For thermal equilibrium, 2 points you need to understand. The first one, when two objects are in thermal equilibrium, they must have the same temperature. And the second, no net flow of thermal energy between them. no net flow of thermal energy. Then we can say two bodies are in thermal equilibrium. No net flow of thermal energy. So these 2 points you have to mention in your answer. But this is very important one. Net. There is flow of thermal energy between objects when are in thermal equilibrium. But there is no net flow of thermal energy when objects are in thermal equilibrium. So net is very important. Now let me show you how you can write down your answer. So this is how you can write down your answer. You can say two objects are in thermal equilibrium when they are at the same temperature and when there is no net flow of thermal energy between them. So it means that when two objects are in thermal equilibrium, let's say these two objects, they are in thermal equilibrium. So they will be at same temperature. There will be flow of energy between them, but there is no net flow of thermal energy. Means they're losing the same amount of thermal energy. Losing and gaining the same amount of thermal energy. Now if we go to the second question. For the second question, it is given to us the mass of the ice is X and the ice is at 0 degree Celsius and it is placed in a beaker containing m mass of water at temperature T. And it is also given to us the specific latent heat of fusion of water is L, the specific heat capacity of water is C, the final Celsius temperature of the system is theta. Give expressions in terms of sum or all of X, M, T, theta and L and C for the thermal energy. First of all, gained E1 gained by the ice as it melts to become water at 0 degrees Celsius. So in this case we have ice first of all, so we can simply say this is ice, this is 0 degree Celsius. Then it is melted to water, so this is water, and water is also at 0 degrees Celsius. So what is happening in this case? Phase change. So specific latent heat. Specific latent heat Q, that is equal to m times L, and in this case mass of the ice is X, so this is simply X times L. M is the mass of ice melted, so in this case we are assuming all the ice has been converted into water. Very important one. This is mass of solid, mass melted, I will simply say melted, meaning it is converted into water. Now the second part, E2 lost by the water as its Celsius temperature decreases from T to theta. So in this case temperature is decreasing, so specific heat capacity, and specific heat capacity Q is equal to mc delta T. So we need to find out how much heat is lost. So this is mc, but m in this case has to be mass of water. So this is mass of water times specific thermal capacity of water times the change in temperature, means the initial temperature, because its temperature is dropping, so in this case you will get positive answer. If you write theta minus T, your answer will be negative, means it is losing thermal energy. So this is simply T minus theta. So this is initial temperature, this is final, so this will give us positive answer. But if we use theta minus T, final temperature minus initial, our answer will be negative. That also represents that water is losing thermal energy. So this is how you need to understand and how you need to answer this question. So the answer for this question is capital M, small c, so we can say T minus theta. Third part says E3 gained by the melted ice as its Celsius temperature increases from 0 degrees Celsius to theta. So now in this case temperature is increasing, so this is about specific heat capacity, thermal capacity. So simply we need to understand Q has to be equal to mc delta theta. So in this case we are talking about ice, so the mass of ice is X and the specific heat capacity is C, and the rise in temperature from 0 to theta, so this is theta minus 0. So simply we can say this is equal to xc times theta. So this is our final answer. So it is very important at this level to read question carefully and then try to connect with your understanding of physics. Then you will be able to answer these questions. Question C says, use your answers in B to show that the final Celsius temperature theta of the system is given by this expression. Using your answers from B, very important one. It means what we have done in part B, now that is kind of hint for us, and we have to use that working from part B to answer part C. And also, as question said, you have to use, so you have to follow the instructions given in the question. So in the last part, we have seen that the heat lost by the water, so we have found that E2, the heat lost by water, so we can say the heat lost by water, this is equal to the heat gained by ice, so we can say gained during phase change, so heat gained by ice during phase change, so this is one thing you can write down, during phase change by ice, plus energy gained by ice when temperature rising, gained when temperature rises. So this is in a systematic way, you need to understand when temperature rises from 0 to theta. So we can say temperature rises. So heat lost by water was E2. Heat gained when the phase was changing, that was E1. And when temperature of the ice was rising, when it was in liquid form, so that was E3. And E2 we have found, that is mc times T minus theta in the last part. And E1 was XL and E3 was XC times theta. Now at this point, what we need to find out? We need to find theta. So we have to separate. So the terms including theta should be on one side and without theta on other side. So we need to multiply inside. So we can say this is mct minus mc theta plus, so this is equal sign here. So this is equal to XL plus XC theta. Now we have this minus, we can bring on the other side, so we can rearrange. We can say this is MCT and this we can take on left side. So this is plus, so here it will be negative. This is negative on this side. This one will be positive. MC theta plus XC theta. Now here we can take theta common, so we can write down here, we can take theta out. So what is left inside? We have MC, but we can also take C out because C is also common, so we can take C also out. So what is left inside? So this is M plus X, and here we have this is MCT minus X times L. Now finally we can write down theta. This one will be equal to MCT minus XL divided by C times M plus X. So simply you need to understand, you need to take the terms containing theta on one side and other terms on other side, then just solve for theta. So this is our final answer, and this is the same as given in the question. So this is our final answer. Third question, part A says, what is meant by an ideal gas? A gas that obey PV is equal to nRT. That gas is ideal gas. And this gas has to obey this equation at all values of P, V and T. But T is a special temperature. So this is not temperature in degrees Celsius. This is thermodynamic temperature, means temperature must be in Kelvin. Then this equation is valid. Otherwise, this is not valid. So in the answer, first thing you have to say PV is equal to nRT. It has to obey this equation, and this has to be obeyed at all values of PV and T. And T you need to specify is thermodynamic temperature. Now let me show you the answer, how you can write down the answer. So this is how you can write down the answer, and these points you have to mention in the answer. So this is very important one. PV is equal to nRT. Most of the students, they will write this one, but they will not write this. Then also they will not clarify what is T in this equation. Part B says an ideal gas at a pressure of 1.6 times 10 to 5 pascals has a density of 1.9 kgs per cubic meter. Show that the root mean square speed of molecules of this gas is approximately 500 meters per second. So what is given to us? Value of P is given to us and the density is given to us. So we need to find out root mean square speed of molecules. So we need to find the relationship between P and density. But in the formula list, it is given to us that PV, this is equal to 1 by 3 Nm times mean square speed. We need density. So we need to understand what this term is representing. N times M. M is the mass of single molecule, N is representing number of molecules. So this is the total mass. So this is representing total mass of the gas. So we can say PV is equal to 1 by 3, so I can write on capital M. So this is the total mass of the gas time mean square speed. So now if we divide mass by volume, that is density. So we can divide M divided by V. So this is mass of gas and this is mean square speed. Now if we simplify this one, so we can say this is density of the gas and here we have mean square speed. So we need to find out the root mean square speed, so we can rearrange this again. So we can write down this is mean square speed. This will be equal to 3p divided by the density of gas. But we need root mean square speed, means we need to take the square root of this one. So this is over VRMS, or you can say CRMS. So this is CRMS. So we have to take square root on both sides. So this is 3p divided by 10. So this is the equation. Now simply we have the values, they are in SI units. So here we have 1.6 times 10 to 5 and we have to multiply by 3 and we have to divide this one by density of gas 1.9, and now simply we need to solve. If we solve this one, we will get 503 meters per second. So this is approximately equal to 500. So we can say this is approximately equal to 500 meters per second. So this is the final answer. So this is how you need to approach. So the main takeaway is this equation is very important one. Most of the time you will need this one. And also you need to understand average kinetic energy of the molecules. Average kinetic energy, translational kinetic energy of the molecule is equal to 3 by 2 K times T. So this is equal to 1/2 M mean square speed, and this is 3 by 2 K times T. This is also very important one. So you have to be clear about this one as well. And two more equations are very important one. PV is equal to nRT and PV is equal to nKT. So from here you can see nRT is equal to nKT. So these relationships are very important one. So you need to understand how to play with these equations. Second part says one molecule of the gas has a mass of 4.7 times 10 to negative 26 kgs. Determine the thermodynamic temperature of the gas. So now mass of one molecule is given to us and we have already found value of CRMS. CRMS that is equal to 500. So you have to use the exact answer, not the approximated one. So we got 503 meters per second. And mass of one molecule is given, and we need to find out thermodynamic temperature. So which one we can use for that? I have told you these equations are very important one. 1/3 nm times mean square speed and 1/2 m times mean square speed. This is equal to 3/2 k times t. And k is a constant, Boltzmann constant. So which one we can use? And also we have PV that is equal to nRT. We have PV that is equal to nKT. Now if you look at these equations, I hope you will simply say this one is the right one. So we can use this because this is mass of one molecule and this is mean square speed. So we have value of C. So K is a constant, temperature we can find out. So simply we can write on here 3/2 K times T. This is equal to 1/2 m times mean square speed. So these two simply we can cancel. So we need to find out T. So this will be equal to m times mean square speed divided by 3 times K, and we don't need square root. So now simply we need to plug in values. M is the mass of single molecule, that is 4.7 times 10 to negative 26, and value of C, this is equal to 503 square divided by 3 times 38 times 10 to minus 23. So if we solve this one, we will get 288 Kelvin. So up to 2SF, as this data has 2SF, so our final answer can be 290 Kelvin. So you can say 290. So this is how you need to answer. Part C says calculate the internal energy U of 6.0 moles of gas in B. Explain your reasoning. So now in this case we need to find out the internal energy of the gas. Internal energy, but we have the formula that kinetic energy, translational kinetic energy of the molecules, this is equal to 3/2 K times T, and this is kinetic energy of single molecule. So very important one. So you need to understand this is kinetic energy of single molecule. So we need to calculate the internal energy, and internal energy is the sum of kinetic energy and potential energy. In this case we are talking about ideal gases. So ideal gases, they do not have intermolecular forces, so they do not have potential energy. So the internal energy is only due to kinetic energy of the molecules. So we can say internal energy will be equal to, this is one molecule, so we have to multiply with number of molecules, n. So here we also need to multiply by n. So we can say the internal energy will be equal to 3/2 nk times T. But we don't have value of n. To make it simple, we have number of moles. So we can compare these two equations. PV is equal to nRT and PV is equal to n times K times T. So simply we can replace now nKT with nRT. So we can write down here 3/2 n times R times T. Now simply we need to plug in values and we can find out value of internal energy. So we have 3/2 and number of moles we have 6.0, and value of gas constant, universal gas constant, is 8.31, and value of temperature we have found in the last part. We need to use the exact value, that was 288. So if we solve this one, we will get 2.16 times 10 to the power of 4. So this is our final answer. This is how you need to answer. Question 4, part A says, what is meant by a simple harmonic motion. And this is very common question in the exam paper. So we have to be clear how to state what is meant by simple harmonic motion. For simple harmonic motion, there are certain conditions need to be fulfilled. The first one is acceleration is directly proportional to x. And the second, acceleration and displacement, they are in opposite directions. Means when one is positive, other one has to be negative. When this one is positive, this is positive, this one has to be negative. And when this is positive, this one has to be negative. So this is the second. And acceleration is always directed. Acceleration is directed towards mean position. So these are the main points you need to understand. Towards mean, or we can say equilibrium position. So based on this one, we can define simple harmonic motion. Now let me show you how you can write down the answer. So this is how you can write down the answer. So in the answer, you can mention particle where the acceleration is directly proportional to its displacement from the fixed equilibrium position and is always directed towards that position. Part B says a small sphere is suspended from a fixed point P by a string of negligible mass as shown in figure 4.1. The sphere is given a small horizontal displacement and is then released. On the next page, we have the graph. So this graph is given to us. On this graph, you can see on y-axis we have the velocity and on x-axis we have the time. Part 1 says state two times at which the sphere is passing in the same direction through the equilibrium. Now at this point, first of all, let's say when the sphere is moving this way. So this is the negative direction we are taking. This is negative. So it will go this way, then it will come back. So when it will come back, so this will be positive. Let me redraw this one for better understanding. So first of all, let's say it's moving this way. So this direction we are taking as negative. So it will go this way, it will reach the extreme position, then come back. So now at this point, moving to the right, so this one we will be taking positive, so it will reach the extreme position and then it will come back again. So you can see this is one complete cycle. So the velocity should be negative and it has to be after one complete cycle. So this is negative case. We can also consider positive case as well. So for example, at this point, velocity is negative. Again, after one cycle, it will be negative at this point. So the time is t1, time is t5. So this is if you take the negative. But you can also take the positive one. So we can redraw when we take the positive. So let's say, first of all, sphere cross this point. So it's moving to the right. So this is positive. So it will reach extreme, then it will come back. Now it is moving to the left, so this is negative. So it will reach extreme, then again it will cross this equilibrium. So it is again in positive. So you can see this is again one complete cycle. So you can take this point, it is positive, T3, equilibrium, so maximum speed. So here T7, again positive. So you can write any of them. So I'll be just writing T1 and T5, but you can also write down T3 and T7. Both answers are correct. For the second part, question says the time interval between T1 and T6 is 2.2 seconds. Calculate the frequency of oscillations of the sphere. So T1 and T6. So T1 is located here and T6 is located here. So we can see from here, so this is one complete cycle. So this is one complete cycle. And this is 1/4. So this is, so we can draw the line here. This is one complete cycle and this is 1/4. So this has time equal to one time period and this has time equal to T/4. So it simply means that T plus T/4 4. This is equal to 2.2 seconds. So simply we can say this is 5t divided by 4. This is equal to 2.2 seconds. So from here we can find out t, that will be equal to 1.76 seconds. Now we have time period, so we can find out frequency. Frequency is the reciprocal of time, so we can say 1 over t, time period, and time period is 1.76. So we will get in this case 0.57 hertz. So this is the frequency. Part C says the sphere in B is undergoing simple harmonic motion. Use the answer in B2 and data from figure 4.2. So this is figure 4.2. Determine the maximum displacement of the sphere from its equilibrium position. Maximum displacement. So we need to understand the Vmax, the maximum velocity, is equal to angular frequency times maximum displacement, means amplitude. So we need to find out the value of A. So this is simply equal to Vmax divided by omega. And Vmax we can read from here. This is equal to 0.08 and omega is equal to 2 pi f. So we can write down 0.08 and we need to plug in value of frequency. We have found in the last part that was 0.57. So the final answer will be 0.0224. So as data has 2 SF, so simply we can write the final answer up to 0.022. So this is our final answer. Question 5, part A says define electric potential at a point. An electric potential at a point is defined as the amount of work done to bring a unit positive charge from infinity to a point, to a certain point. Work done per unit charge. So we can say per unit charge, but it has to be per unit positive charge. So how we can define it? So this is how you need to answer. In the answer you need to mention at a point is the work done per unit positive charge. So it's better to write down positive. Don't miss this one. In bringing a small test charge from infinity to that point without acceleration. Part B says an isolated solid metal sphere of radius r is given a positive charge. The potential at the surface of the sphere is 9.0 times 10 to 4 volts. At a distance of 3r from the center of the sphere, the electric field strength is 2.0 times 10 to 5 newtons per coulomb. Determine the electric field at the surface of the sphere. So first of all, simply we can imagine this one is a sphere and the radius of this one is given, that is r, and at this surface we need to find out what is value of E. And at certain point, distance 3r means when the distance from the center of this one is equal to 3r, value of E is given, we can say this is E1 and this value is 2.0 times 10 to 5 newtons per coulomb. And so how we can answer this question now? So for this question simply we can write down the equation for this one for the surface. So we can say E, this one has to be equal to kq over r square and E1 has to be equal to kq over, so we have this is 3r square, so we can say this has to be equal to kq over 9r square. Now in this case let's say this is equation 1, this one is 2. Now if we simply divide equation 1 by 2, so we will get E divided by E1. So this is E1. So this will be equal to kq over r square multiplied by 9r square divided by k times q. So simply you can see these two quantities, they will be cancelled. So we left with this r square, we can cancel with this one. So what is left behind? 9. and here we have E divided by E1. So what we need to find out? We need to find out E. So this is 9 times of E1, and value of E1 is given to us. This is value of E1. So just multiply. So we have 2.0 times 10 to 5. Now if we solve this one, I'll be writing here. So if we solve this one, we will get 2 times 9, 18. So this is 1.8 times 10 to 6 newtons per coulomb. So this is our final answer. For the second part, we need to show that the radius of the sphere is 5.0 centimeters. But in the last part, it was given to us that the value of the potential is equal to 9.0 times 10 to 4 volts, and value of E we have also find in the last part, that was equal to 1.8 times 10 to 6 newtons per coulomb. So how we can use these two values and we can find the value of R? So for this one, we need to understand is that this is our sphere. So the charge at the surface of this one, let's say the charge is Q at the surface of this sphere. So we can write down V, that will be equal to KQ over R, and E, this is equal to KQ over R square. Now you can see from here KQ will be cancelled. So if I simply divide, let's say V divided by E, V divided by E, so it means KQ over R multiplied by R square divided by K times Q. Q is the same. This is the charge on the surface of the sphere. This is the charge on this sphere. So KQ will be cancelled. So R, so we left with R. So simply in this case, R is equal to V divided by E. So simply we can plug in values. So we have V, that is equal to 9.0 times 10 to 4 and divided by 1.8 times 10 to 6. And if we solve this one, we will get 5.0 times 10 to minus 2. So it means this is simply 5 centimeters. So the better way of writing this one is, this is 5.02 SF centimeters. So this is the answer. For our third part, we need to calculate the charge on the sphere. Means we need to find out what is value of this Q. This is the charge at the surface of sphere. So to find this one, we can use V or we can use E. But for simplicity, I'll be using V. V is equal to KQ divided by R. So we need to find out value of Q. So simply we can say this will be equal to VR divided by K. And value of V, we have that is equal to 9.0 times 10 to 4 multiplied by R. So we have found 5.0 times 10 to minus 2 divided by K, that is equal to 8.99 times 10 to 9. So if we solve this one, we will get 5.0 times 10 to negative 7 coulombs. So this is the value of charge, 5.0 times 10 to negative 7 coulombs. Part 4 says use the answer in B theory to determine the capacitance of the sphere. And Q is equal to CV. From here we can say C is equal to Q over V. So if we plug in V is equal to Q over 4 pi epsilon naught times R. So we will get 4 pi epsilon naught times R. So this is the C. So we can say C is equal to 4 pi epsilon naught times R. But we also need to understand that K is equal to 1 over 4 pi epsilon naught. K is equal to this one. And the value of K is equal to 8.99 times 10 to 9. So from here we can say that 1 is equal to 8.99 times 10 to 9 times 4 pi epsilon naught. So 4 pi epsilon naught This is equal to 1 over 8.99 times 10 to 9. Let me write down this one in a nicer way. So this is a better way to say it. This is 4 pi epsilon naught. So we can replace here 4 pi epsilon naught. This is equal to 1 over 8.99 times 10 to 9 multiplied by the radius of the sphere, that is 5 times 10 to minus 2. So if we solve this one, we will get 5.56 times 10 to minus 12. So this is value of capacitance, and the unit of this one is farad. So we can write down here 5.56 times 10 to negative 12. So this is the answer, and that's all for today's questions. We will just stop here. So we have done 5 questions. First 5 questions we have done. 4 questions in this video and 1 question in part 1. I have explained these questions in detail, and I hope these questions will help you to improve your understanding of physics. And also, if you are looking for extra resources, mean the PDF of these papers with detailed solution, not only the mark scheme and other resources, topic-wise questions and more, you can check Patreon, and the link for Patreon is in the description of this video. And if you have any questions, please leave your questions in comments, and I will try to answer as soon as possible. And also on the channel you can find a lot of videos. I have solved at least 60 past papers for Cambridge A-level physics, and you can find all the papers on this channel. See you in next video. Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from May-June 2025, Paper 4, Variant 4. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of physics, and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question 6 says a rectangular coil PQRS of wire is free to rotate about its axis XY as shown in figure 6.1. So we have a coil that is rotating about its own axis XY, and the coil is PQRS. The length of QR is given, that is 5.4 centimeters, and the length of PQ is 2.5 centimeters, and this coil has 190 turns of wire. And the magnetic flux density is also given, that is equal to 5.2 times 10 to minus 3 Teslas. The axis XY of the coil is normal to the field. As you can see, this angle is normal, means the angle between the axis of rotation and the magnetic field is 90 degrees. Current in the coil is given is 1.2 amps. We need to calculate the magnitude of the force on side QR of the coil. Side QR, very important. So you need to read question carefully. Side QR. So this side is QR. So this side is QR. So this is, you need to understand. Now you need to understand is that here it is very hard to figure out the angle between the magnetic flux density and this side. But if you look at this one, this view, the end view, so here is like this one, this geometry box, you can see first of all it is placed like this. Now it is like this. So this side is QR. So current in QR, if you look at this one, current will be into the page. So this is what you need to imagine. This is what you need to understand. Current is into the page and magnetic field is to the right. So what is the angle? Let me explain you this one with these two markers. So current is into the page. So this is pointing, current is into the page, and magnetic field is to the right. So what is the angle between these two? Angle is 90 degrees. So simply you need to understand angle is 90 degrees angle between B and I. So we can say that theta between B and I, this theta is 90 degrees. So we can say it's 90 degrees between B and I. So we need to find out the magnetic force, that is equal to F is equal to BIL sine of theta. Theta is the angle between B and I. So theta is 90, so sine 90 is 1. Now simply we can plug in values. So value of B is 5.2 times 10 to negative 3, and value of I is given, that is 1.2 amps, and the side of this length QR, that is 5.4 centimeters. So this is 5.4 centimeters, so 10 to minus 2, and sine 90, so here we have sine of 90 degrees. Now if we solve this one, we can find out value of force. That one will be equal to 0.064 Newton. So this is how you need to figure out. So the main point is to find out this angle, the angle between P and I. So you can visualize, you can place marker, so you can see current is into the page, magnetic field is to the right, so angle is 90 degrees. Second part says, use the answer in A1 to show that the torque on the coil is given by 1.6 times 10 to minus 3 cosine of theta, Newton's meter. So first thing we need to understand is that what is the torque of a couple? Torque is equal to force time perpendicular distance between line of action of two forces. So if you look at this, here we have two forces acting on two sides. One force is acting down, another force is acting up. So actually here is a force that is acting down, and here is a force that is acting up. So you need to be clear about this one. So this is F, this is also F. We have already said this one is L. So we can say this side is W. So it means this is W. And what is the perpendicular distance? Perpendicular distance is, if I draw this line of action of forces, so here you can also extend this one for your better understanding. So this distance is perpendicular distance between these two line of action of forces. If this is W and this angle is theta, so this angle also has to be theta. So it means this D perpendicular distance is W cosine of theta. So torque is equal to force time perpendicular distance. So in this case we have n number of coils, so we will multiply with n. Force is equal to PIL, and perpendicular distance is W cosine of theta. W cosine of theta. So now you can see from here what this LW is representing. LW. So this side is W, so this is W, and this one is L. So it means that this is representing this area. So we can say it is representing this area. So simply we can replace this now with area. So we can say this is NPIA cosine of theta. Now simply we need to plug in values and we will find our answer is equal to this. So we can rewrite here tau, this is equal to NPIA cosine of theta. We don't need value of theta because theta is in the answer. So what is N? N is 190. And what is the value of the B? The flux density, that was equal to 5.2 times 10 to minus 3. And in this case we have area, that will be equal to 0.054 times 0.025. This is area, and value of current is 1.2 amps, and here we have cosine of theta. Now if we just multiply, we will get 1.6 times 10 to minus 3 cosine of theta, and the unit for torque is Newton's meter. So this is our final answer. This is how you need to answer. But one more thing you need to understand is that whenever you need to find out torque on the coil, Means when you need to find torque on the coil, you no need to go through all these steps. Simply you need to understand tau is equal to NBIA times cosine of theta, and theta is the angle. So let me show you what is the theta in this case. Theta is the angle between magnetic field and the plane of the coil. This is the plane of the coil. So this is the angle between B and plane of the coil. So we can say plane of the coil. So you can simply plug in values and you can find the answer. Third part says use the expression in A theory, sketch on the axis of figure 6.2 a graph to show the variation of the torque with angle theta for values of theta between 0 and 360 degrees. Label the tau axis with an appropriate scale. So for this one we need to understand first of all when tau is maximum. So tau will be maximum. So we can say tau will be maximum at theta is equal to 0. When theta is equal to 0, so what is the maximum value of the tau? In the last part we have done tau is equal to 1.6 times 10 to minus 3 cosine of theta. When cosine of theta is equal to 1 means cosine of 0 is equal to 1. So this is maximum value of tau. We need to use appropriate scale. So we can say this is 1 and this is 2. So this is very nice scale because our maximum value is 1.6. So it is lower than 2. So now we can locate the maximum values. This is 1, so 1.6 will be 1, 2, 3, 4, 5, 6. It is at this point. And when cosine 90, it has to be 0. When cosine 180, it has to be maximum but negative. 1, 2, 3, 4, 5, 6. So about this point. 270. 0, 360 maximum. So we can say 1, 2, 3, 4 at this point. So simply we need to sketch this one, connecting these points. So if we connect these points, our shape should look like this. So this is how we need to sketch. So this is how we need to sketch. I hope this makes sense to you. So these points are important. So this point, this is what is this value? 1.6 times 10 to minus 3. This value is also the same. Here it has to be 0. Again, maximum at this point. So this is how you need to answer. So the shape of the graph is determined by cosine of theta. So that's the reason this is cosine graph. Part B says the coil is now replaced by an identical coil wound on ferrous core. Suggest with a reason how the torque on this coil compares with the torque on the original coil. Now it is ferrous core now, and ferrous is a magnetic material. So you need to be clear about this one. Ferrous is a magnetic material, and when the magnetic material is in the magnetic field, it also becomes a magnet. So in this case, it means value of B will increase. N is the same, I is the same, A is the same. So if B increase, what will happen to the torque? Torque will also increase. So this is how you can answer. Now let me show you the answer, how you can write down in a proper way. So this is how you can write down the answer. So you need to say, first thing you need to say, the torque increases because ferrous core increases the magnetic flux density. This increases the force on the coil, so resulting in a larger torque. So 2 points are very important. First thing, ferrous core increases the magnetic flux density. So this point has to be in your answer. Then you need to also state it will increase the torque. So these 2 points at least has to be in your answer. This is also an important point. So it's better to use these 3 points, you can say. these theory points. Question 7 says a bar magnet is suspended from a spring. One pole of the magnet oscillates freely in a coil of wire as shown in figure 7.1. So this figure is very common about oscillations and electromagnetic induction. So you have to be very clear about this one, means you need to listen this question carefully to have good understanding of this type of problems. And this is very common one. The switch S is initially open. The switch S is now closed. As a result, the oscillations of the magnet are lightly damped. For part A1 state what is meant by damping. So what is damping? So in a simple language we can say damping is loss in energy. So we can say damping is loss of energy. It causes loss of energy. And loss of energy is due to resistive forces like friction, like air resistance. So we can say due to resistive forces, and it is also due to magnetic forces. And due to this one, amplitude decreases. So these are the points you have to be clear about damping. So we can say amplitude decreases. And now we can write down these points in a nicer way. So this is how you can write down the answer. So in the answer we have said where energy is gradually removed from the oscillating system causes the amplitude of oscillations to decrease. This happens due to resistive forces. So these are the key points you have to mention in the answer. Second part says describe what is observed to indicate that the damping is light. So we need to understand what is light damping. In light damping, amplitude decreases gradually. So this is the main point you need to understand. Amplitude decreases gradually over time. Gradually is very important one. So this has to be in your answer. You cannot simply say amplitude decreases. Gradually with time, or you can say over time. So this is the main point you need to mention. If you write on this one, you will get 1 mark. Then also you need to understand in light damping, frequency does not change. Our time period almost stays the same. Almost, little bit slightly change, but it stays the same. Frequency actually slightly decrease, or you can say time period little bit increase, but that is negligible. Now let me show you how you can write down the answer. So this is how you can write down the answer for this question. Third question says by reference to electromagnetic induction and to conservation of energy, means you have to use conservation of energy and electromagnetic induction concept in your answer. Explain why the oscillations are damped in this case. This question also can be explained using the concept of forces, but they have specified you have to use conservation of energy. So in this case, as magnet is moving up and down, there is a change in flux. There is change in flux in the coil. So change in flux in the coil. As there is just change in flux in the coil, there will be induced EMF. So I'll be writing this way. There will be EMF induced in the coil. So we are talking about coil. As coil is a complete circuit, so we can say then as it is a complete circuit, coil is a complete circuit, so there will be current in the coil and current will pass through the resistor. So then electrical energy will be converted when current passes through the resistor. Electrical energy will be converted into thermal energy, and this energy, electrical energy, is converted from mechanical energy of the magnet into electrical, and then electrical is converted into thermal energy. So this is based on conservation of energy. So in this case, magnet is losing mechanical energy, amplitude will decrease because its mechanical energy is decreasing. So that's the reason these oscillations are damped. There is no free energy. Most of the machines, they convert energy from one form into another form, and with the help of electromagnetic induction, we also convert energy from one form into electrical. So this is the main idea. Now let me show you how you can write down answer in a nicer way. You can mention about electromagnetic induction, as we have discussed here. As the magnet moves, it induces an EMF in the coil. Then we can talk about current and energy dissipation, as we have discussed current here. So this is energy dissipation, electrical energy into thermal energy. Closing the switch, current will flow, dissipating energy as heat in the resistor. Conservation of energy, the kinetic energy of the oscillating magnet is converted into thermal energy. That's the reason amplitude will decrease over time. So this is how you need to answer. This also can be answered based on forces. You can think about this one, how we can answer this one based on forces. Part B says the procedure in A is repeated after replacing the resistor with one of greater resistance. Suggest with a reason the effect of this change on the oscillations. Now what is the effect? So in this case, procedure is repeated, means it is moving at the same speed. So in this case, we can say the power P will be equal to V squared divided by R. This is the power lost in the coil, means electrical energy converted into thermal, or you can say mechanical energy converted into electrical per second. This is the EMF, so we can say this is the EMF divided by R. EMF does not depend on the resistance. So EMF in this case is the same. So if R is increased, it means power loss will decrease. So what does it mean? It means less damping. Less damping. So this magnet will take longer time to stop. We can also explain this one. P is equal to I square times R. So as current in this case will decrease, so the power will also decrease, power loss will also decrease. So this will take longer time to stop. So amplitude will decrease slowly. These are the points we need to answer this question. Now let me show you the answer, how you can write down a nicer answer. So this is how you can answer this question. So you have to mention increase in resistance will reduce the current. So current will be reduced. If the current is reduced, it means energy dissipation will decrease. And due to less loss of energy, damping will decrease and it will take longer time to stop. So these are the important points. So this is what you have to mention, and you also have to mention this point, and then you will say less damping in this case. So that's all for this video. I hope you have a better understanding of these questions. And if you're looking for more resources, or if you need individual help, you can check Patreon, and on Patreon you will see a lot of resources, PDF of these solutions, revision guides, topic wise questions, and much more. I will try to upload the remaining questions as soon as possible. And if you have any questions, please leave your questions in comments and I will try to answer as soon as possible. Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions from May June 2025, Paper 4, Variant 4. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of physics and also you can have better understanding of these exam questions. Let's study together, let's improve together. In question 8 says, an incomplete circuit diagram of a bridge rectifier is shown in figure 8.1. Complete figure 8.1 for the bridge rectifier such that the point A is set at positive potential with respect to point B. So this one has to be positive, this one has to be negative. So how we can draw the diodes? We need to draw the 4 diodes. So one thing you need to understand is that I often used to tell students the side where diodes converge, that is positive. From where they diverge, that side is connected with negative. So diverge. So diverge means this means diverge. This means diverge, and this means converge. So if you have this understanding, now you can draw the diodes. So this is simply how you need to draw. This has to be complete, no gap in your diagram. Diverge. So here these two, they have to diverge. So this is how you can draw. They have to diverge. So we can draw here. Diverge. So here they have to converge. So this is how you can draw. They have to converge. So here also has to converge. So we can draw. They have to converge. But there shouldn't be any gap. So this is how you need to draw. So you can also see when this side is positive, how current will flow. It will flow this way, but it cannot go this way because this is in reverse biased. So current will go this way. It will pass through this one, then it will enter resistor from this side. So the entering side of the resistor is positive. So it will flow like this, then it will go like this, and at this point current cannot flow this way because this point is at high potential and this point is at low, and current cannot flow from low to high. Always current flow from high to low. So current will not go this way. So it will pass through this diode and come back. So simply you no need to draw these dotted lines. So you need to draw these 4 diodes. Part B says the variation with time t of the potential difference V across the load resistor is shown in figure 8.2. The capacitor is now connected between points C and D of the bridge rectifier. This results in a smoothing of the PD across the load resistor. The difference between the maximum and minimum values of the smoothing PD is 33% of the peak value. On figure 8.2, draw a line to show the variation of the PdV across the load resistor with time t. Mean we need to draw at least from here to here. So the difference between maximum and minimum is 33%. So 100 if we divide into 3 parts, so we can say the V min, minimum value of V, this has to be equal to 2 by 3 of V naught, and the V max, this will be equal to V naught. So these are the points we need to understand. Now we can count the squares. So if you look at this point, we have 10 square here and 5. We have total 15 squares. So it means that 2 by 3 times 15 mean V naught is represented by 15 small square. So how about the V min? This will be represented by 10 small squares. So we can say 10 small square. So these are the points you need to understand to sketch the graph. So it means it will drop from here to this point. So it will drop like this. So let me draw in a proper way a little bit. So actually it's a curve, exponential decay. It will decay like this. Then it will rise. So here it will fall to this value. Then it will rise. It will fall to this value. It will rise. Then it will fall to this value. Then it will rise. Then it will fall. And so now simply we can from here exponential decay. Then here it rise to maximum value. Then exponential decay, and then again it will rise to maximum value, then again exponential decay, and then it will rise to maximum value, and then again it will decrease. So somewhat here it will decrease. So this is how we need to draw. Second part says use your line in B1 to determine in terms of capital T, means in terms of time period, the time constant of the smoothing circuit. If you look at this diagram, we can see the maximum value is V naught and our capacitor is discharging here. You have to be clear, capacitor is discharging here. So we can say capacitor is discharging here from this point to this point. Capacitor is discharging, and then from here to here capacitor is charging. So this red one is representing capacitor is charging. To find the time constant, we can use this discharging part. So if we draw the line here at this point, so we can see the number of small squares, these are 11, and total number of small square for one time period, we have 10 here, we have 20 here, so 30. So we have 30 small squares. And the value of V after discharging of capacitor means the minimum value, that is equal to 0.67 V naught. This is 2 by 3 of V naught. Now simply we can use the discharging formula. V is equal to V naught e to the power of minus t over tau. So what is the t here? Time taken from here to here. We can write on this one in terms of time period. So time period is equal to 30 small squares, and here we have 11, so it simply means that this is 11 by 30 of time period. So this is the time taken from V naught to 0.767 V naught. So this time is t. Now we can simply plug in values. So here we have 0.67 V naught. This will be equal to V naught e to the power of minus t over tau. But t we can replace with these values we have done. So we can simply say, in this case, this is minus 11 by 30 times capital T. And this V naught we can cancel with this V naught. So simply we left with 0.67. This is equal to e to the power of minus 11 by 30 times capital T, and this is divided by tau. Now we can take natural log on both sides, ln, so we have 0.67 ln. So here ln is 1, so what we will get minus 11 over 30 times t, and this is divided by tau. We need to find out value of tau. So tau we can multiply on other side, so this is 0.67. So we can also write on this one tau. This will be equal to minus 11 t by 30 divided by ln. So here we have ln natural log of 0.67. So simply just basic mathematics. Now if we plug in values, we will get in this case 0.36 t. This is divided by 0.40, and if we simplify this one, we will get 0.92 capital T. So this is how we can find out value of tau. I mean, this is the time constant actually for the capacitor, discharging capacitor. This is how we can figure out. Third part says the resistance of the load resistor is now increased. The capacitance of the capacitor is unchanged. State and explain the effect of this change on the smoothed output PD. So what is the effect on output PD? Or we can say what is the effect on ripples. So for this one, as the resistance of this load resistor is increased, and our capacitor is connected between C and D, so capacitor is connected here. So capacitor will discharge through this resistor. So tau for discharging is equal to RC. So if resistance increased, C remains constant, so tau will increase. Tau increase means that capacitor will discharge slowly. Capacitor discharges slowly. So what does it mean if capacitor discharges slowly? If capacitor discharges slowly, so we will see the curve somewhat like this. So this means capacitor is discharging slowly. So this will be the new curve. So we can draw like this. Capacitor is discharging slowly. So this is how curve will look like. So the ripples, you can see the variation in PD, it has decreased. First of all, variation in PD across load resistor was this much. This was the delta V, but now is just this much. So it means variations in ripple will decrease. Variation in PD decrease means ripples will decrease. So these are the points you need to understand to answer the question. Now let me show you the answer, how you can write down a nice answer. So in your answer, you have to include these points. So first of all, you can say as R increases, tau will be greater. As tau is greater, it means capacitor discharges slowly, so the ripples will decrease. Question 9 part A says, describe what is meant by wave-particle duality. Wave-particle duality means that waves can behave like particles. They can exhibit particle-like behavior, and particles like moving electrons, they can exhibit wave-like behavior. So this is wave-particle duality. So waves, we can say, they can exhibit like particle-like behavior. So we can say particle-like behavior, and particles can exhibit like wave-like behavior. So we can say particle, moving particles, very important one. Moving particles can exhibit wave-like behavior. Yes. American or UK, same. So behavior. So these are the points you have to write down in your answer. Now let me show you the answer. So in the answer, these points you have to mention. So if you have mentioned wave particle duality is the concept. Electromagnetic waves mean the waves can exhibit particle-like behavior, while moving particles can exhibit wave-like behavior. So this means light can act as a stream of particles, mean light consists of photons, and particles like electrons can diffract, they can interfere like waves. Second part says, state the relationship between the de Broglie wavelength of a particle and its momentum p. State the meaning of any other symbols that you use. So simply we need to understand de Broglie wavelength simply is equal to h over p, and p is the momentum of particle, and lambda is de Broglie wavelength, and h is Planck constant. So simply we have to say that h is Planck constant. So this is what you need to say. State the meaning. So Planck constant, and the value of Planck constant you also need to understand is 6.63 times 10 to minus 34 joules second. This is not part of answer, but simply you need to write down h is equal to Planck constant. Part B says a narrow beam of electrons all with the same speed is incident normally on a carbon film. The electrons then move on to a fluorescent screen as illustrated in figure 9.1. The apparatus is in a vacuum. The pattern produced on the screen is shown in figure 9.2. So here we have figure 9.2. Explain why the pattern in figure 9.2. Very important one. Why the pattern in figure 9.2 provides experimental evidence to indicate a wave nature for the electron. So first of all, we have to look at the pattern. So how this pattern look like? This pattern, we have concentric rings. So we can say concentric rings, and these rings are formed due to spreading out of electrons. So we can say due to spreading out of electrons. So we can say due to spreading out of electrons, spreading out. So it means that electrons have undergone diffraction and interference. Diffraction and interference. Diffraction and interference are only the properties of waves. So in this case, electrons behave like waves, or we can say electrons have wave nature, or they are behaving as waves. So these are the points we need to write down in our answer. If you understand these points, now let me show you how you can write down the answer. So we can say, first of all, concentric rings are characteristics of wave interference. This occurs because electrons behave as waves when passing through the carbon film, diffracting and interfering constructively and destructively. So this is how you can answer, and this question has 2 marks. Second part says the speed of the electrons is increased. Suggest with a reason how this change affects the pattern observed on the screen. How this pattern will change if we increase the speed of electrons. So first of all, we need to understand lambda, the wavelength, is equal to h over momentum of moving particle, means momentum of electron, and this is d pro wavelength. So here h divided by m times v. So if v increase, it means lambda has to decrease. So it also means that one more thing you need to understand, lambda is directly proportional to theta. If lambda decrease, it means theta also has to decrease. We can also understand from here, first of all, let's say this is our center fringe, first fringe, bright fringe, and this one is the second, like this. Let's say it is formed like this. But now when we increase the speed, how these bright fringes will form, in this how these rings will form. So first one may be formed here, and the second one will be formed here. So they will be closer to each other, so the angle will decrease. So this is the point you need to understand. Now let me show you the answer, how you can write down the answer. So this is what you need to write down for the answer of this question. You can mention this point. So first you can say higher speed, shorter wavelength. You can also give reference of this formula. So there will be tighter diffraction. So these are the key points. So if you write down, you will get the marks. If you want to explain a little bit more, why tighter diffraction? So this is because lambda is proportional to, theta is proportional to lambda. So if lambda is small, theta will be small. Question 10, part A says, describe how the piezoelectric crystal in a transducer generates ultrasound waves for use in medical diagnosis. Piezoelectric crystal, you can say. How ultrasound waves are produced. So if we have the crystal, so imagine that this one is the crystal, we can apply alternating PD across this one, alternating PD. And the natural frequency of this crystal is in ultrasound range. So the size, the dimensions of this crystal are very important. So when we manufacture this one, so we need to consider the dimensions of this piezoelectric crystal. So its natural frequency is in ultrasound range. So the natural frequency should be in ultrasound rate, means greater than 20 kilohertz in ultrasound range. And when the natural frequency of piezoelectric crystal, natural frequency we can say, natural frequency about equal to the applied frequency of the voltage, applied frequency of the voltage alternating of AC. Then resonance will take place and ultrasound waves will be produced. Resonance takes place. So these are the points we have to mention in the answer. Now let me show you the answer, how you can write down. So in the answer, these points you have to mention. First you can say alternating PD has to be applied, as we mentioned here. So this is alternating PD to the crystal. When frequency of this applied potential difference matches the crystal natural frequency, resonance will take place. This means crystal will vibrate with larger amplitude. Means the maximum electric energy will go to vibrate the crystal. So the amplitude of the sound waves produced, ultrasound waves produced, that will be greater. The natural frequency of such crystal is designed to be in the ultrasound range. Ultrasound range meaning the resonant vibrations produce ultrasonic waves. So when crystal is vibrating, so it will vibrate at the same frequency. So the waves produced, they are ultrasound waves because the frequency is greater than 20 kilohertz. Part B says a parallel ultrasound beam is incident on the boundary between the two media, as illustrated in figure 10.1. The media have specific acoustic impedance Z1 and Z2. At the boundary, a fraction alpha of the incident intensity of the ultrasound beam is reflected. The remainder is transmitted. State what is meant by specific acoustic impedance. So first of all, we need to understand specific acoustic impedance. Z is equal to rho times C. So we can say acoustic impedance is the product of density of medium, very important one. You need to specify which density you are talking about. Density of medium and speed of ultrasound waves in that medium, or you can say speed of ultrasound waves in the medium. So this is how we can state what is meant by specific acoustic impedance. Second part says describe how alpha depends on the relative values of Z1 and Z2. So first of all, we can simply write on alpha. Alpha is equal to Z1 or Z2 divided by Z1 plus Z2 square of this. So if Z1 is about equal to Z2, so what will be the value of the alpha? Alpha will be equal to 0. It means that minimum reflection means most of the waves, they will be transmitted. So we will say minimum reflection. So this is the first thing, minimum reflection. And the second case, what will be the value of the alpha if Z1, for example, or Z2 is much greater than Z2? We can also imagine, let's say Z2 is negligible. So what we will get here, if Z2 is negligible, then alpha will be equal to Z1 square minus, there will be 0, divided by, so let me write down in a better way. So we can simply say this will be Z1 minus 0 divided by Z1 plus 0 square. So what we will get in this case, alpha will be equal to 1. So in this case means maximum reflection. Most of the ultrasound waves, they will reflect back. So we can say maximum reflection. So this question is very common one. So you need to be very clear how to answer this one. Now let me show you the answer. This question has 2 marks, so you can write down these 2 points. Maximum, alpha is about equal to 1 when Z1 and Z2 are very different. And if they are almost the same, alpha is almost equal to 0. Part C says a parallel ultrasound beam of intensity I0 enters the region of soft tissue. After passing through a distance of 2.1 centimeters through the tissue, the intensity of ultrasound is 0.62 I0. Calculate the linear attenuation coefficient mu of ultrasound in the soft tissue. Give a unit with your answer. So in this case, simply we can imagine this one is a soft tissue. This is soft tissue. Incident intensity is I0 when it has traveled distance. Let's say it has traveled this distance inside this tissue. Intensity at this point is 0.62 I0 and the distance traveled is 2.1 centimeters. So we need to find out what is value of mu. So we need to find out what is value of mu. So for this one, simply we need to understand this is kind of exponential decay. I is equal to I0 e to the power of negative mu x. So we can also say this as a function of x for better understanding. But it is given to us when x is equal to 2.1 centimeters, or we can say here x is equal to 2.1 centimeter. If you use 2.1 centimeters, so your answer will be in centimeters. Convert this one into meters, your answer will be in meters. So it depends on which unit you are choosing. So you can use centimeters, you can use meters. So I'll be using centimeters. So let's use centimeters. So here we have value of I at distance of 2.1 centimeters, that is 0.62 I naught. This is equal to I naught e to the power of negative mu x. So I naught we can cancel, so we left with 0.62. This is equal to e to the power of negative mu x. Now we can take natural log on both sides. So we can take ln of 0.62 and ln of e is 1, so we will get negative mu times x. So we can simply say x will be equal to negative ln of 0.62. So if I use this one in centimeters, so I'm using 2.1 centimeters. So our answer will be equal to 0.23 per centimeters. So this is, you can also convert this one into meters. So that will be 23.1 about. So if you convert, that will be equal to 23.1 per meter. So we can write on here, this is 0.23 and the unit is per centimeter. So this is how we can answer. Question 11 says the deuterium nucleus has a mass defect equal to this. The helium nucleus has a mass defect of this. Helium-4 is formed from deuterium in a nuclear reaction that can be represented by the equation. So here we have deuterium nuclei. They combine together and they form the helium nucleus. Part A1 is asking us state the name of this type of nuclear reaction. So as in this case, deuterium nucleus combine to form the helium nucleus. So this is simply nuclear fusion. So we can say nuclear fusion. So this is simply, you need to write down, this is nuclear fusion. But I have written a little bit in detail, so I will show you a little bit detail as well, so maybe you need for your notes. So this is. Second part says, show that the energy released when one nucleus of helium is formed from deuterium is equal to this one. And in the last part, we have the mass defect. So we can find out delta M first of all. So we have deuterium and the mass defect for deuterium is 0.002388 U. This is AMU. And for the helium we have mass defect that was given in the last part 0.03037 U. And if we solve this one, in this case we will get 0.0232130 U. So we got the negative. It means the mass defect in helium is greater than deuterium. So it means energy will be released. So how we can calculate the energy released? Energy released, E will be equal to delta M times C square. But delta M has to be in kgs. So we can simply write down 0.023213 times 1 U. So we need to understand 1 U. Atomic mass unit is equal to 1.66 times 10 to minus 27 kgs. So we can simply write on here 1.66 times 10 to minus 27 kgs multiplied by C square, that is 3.0 times 10 to 8 square of this. Now if we solve this one, we will get 3.47 times 10 to minus 12 joules. So this is how you can find out. You need to understand how to calculate energy released based on given binding energies, based on given mass defect, and also based on mass defect by calculation. So mass defect will not be given to you. You have to calculate mass defect. So you will calculate the mass of reactants minus mass of products. So you can find the mass difference and then you can use the formula. So 3 ways you should be able to calculate energy released based on given masses, based on given mass defect, and based on given binding energies. So this question is based on mass defect. And also you need to understand individual particle like proton and neutron, they do not have binding energy, and also they do not have mass defect. Part B says a star has a radius of 6.96 times 10 to 8 meters. Helium-4 is produced in this star from deuterium at a mass rate of 7.34 times 10 to 11 kgs per second. All the energy released from this process is radiated away from the star. All the energy that is radiated from the star is released by this process. Calculate the luminosity of the star. So what is luminosity of the star? Luminosity of the star is the power of the star, means all the energy radiated by the star per second, or you can say total power radiated by the star. And so how we can calculate the total power? If we have energy released per reaction, so I can say energy released per reaction, so we can say energy released per reaction, and if we multiply with this one with number of reactions taking place per second, so we can calculate power. So these are the points. Now energy released per reaction we have already calculated in the last part, so we can say that is energy released per reaction, that was 3.47 times 10 to minus 12. So this one we have. Now we need to calculate number of reactions per second. So how we can calculate this one? So I'll be writing here number of reactions delta n by delta t. So how we can figure out this number of reactions per second? To calculate number of reactions per second, it is given to us the mass release in 1 second. So simply we can say this is 7.34 times 10 to 11. This is kgs, we can say, per second. And we have mass per reaction. So if we divide this one by mass per reaction, so we will get reactions divided by mass per reaction used. This is mass per reaction, so I have written reactions over mass for your better understanding. So what is the mass of one single helium nucleus? So mass of single helium nucleus. So this one, if we want to write down second, we can write down mass of single helium nucleus, so we can say reactions. Mass is 4 times 1.66 times 10 to minus 27. This is the mass. So this is kgs per second, and this is also in kg. So this is also in kg. So kg cancel. You can see reactions per second we can figure out from here. Now if we solve this one, we will get 1.11 times 10 to 38 per second. So these are the number of reactions per second. So we can write on here 1.11 times 10 to 38 number of reactions per second. Now if we multiply these two together, we will get 3.85 times 10 to 26 watts. So this is the energy released per second. So this is how we can approach. So this is very important one. So try to understand the logic. What data is given to you, how you can use that data to find the answer. So this is, so here I have written number of reactions per second. We have mass per second, how many kgs are released in 1 second, and we have the mass released in one reaction. So I have written mass released per reaction. So you can also say, if you want to write down this one, you can also say this is 1 over, you can say, mass per reaction. So if you understand this way better, mass per reaction, and then we will get number of reactions per second, multiply, and we can find the answer. So the approach you need to understand. Second part says use the answer in B1 to determine the surface temperature of the star. So simply we have to use Stephen-Boltzmann law for this question. Luminosity of a star is equal to A times sigma times T to the power of 4. So this is the surface area. So we can say luminosity, this will be equal to 4 pi r square times sigma times T to the power of 4. So we need to find out temperature. So this will be equal to luminosity divided by 4 pi r square times sigma, and the power of this one 1 by 4. Now simply if we plug in values, we can find the answer. So we have luminosity 3.85 times 10 to 26, and here we have 4 pi, value for r is given to us 6.96 times 10 to 8 square, and we need to multiply this one with Stephen-Boltzmann constant. That is 5.67 times 10 to minus 8. Now if we solve this one, we will get about 5800 Kelvin up to SF. So this is our final answer. So this is how we can answer these questions. We have done this whole paper. I hope you have better understanding of these questions, and if you have any questions, please leave your questions in comments and I will try to answer as soon as possible. And if you're looking for more resources, please join Patreon. On Patreon you will see PDF solutions of these papers, topic-wise questions, revision summaries, and much more. And if these videos are helping you to improve your understanding of physics, please also share with your friends and your classmates. See you in next video.